Okay, so we're doing page 69, torque. And let me just get it up here on the screen. Whoops, wrong one. Where is it? Oh, wrong window. Let me get that over here. Sorry, come on, computer. There we go. And let me do Control F. Come on, man, this is kind of slow right now. Something's going on here. Whatever. All right, there we are. And so our idea is we're going to briefly run through these definitions on page 69, and maybe I'll show you some visualizations for that. And then we're going to just start doing problems. And some of these I maybe have some videos for. So let's, maybe I'll just give you a visual first to give you a feeling for this, because we do have this. I know it's cheesy, but it does the job for most of what we need to see. So I want you to remind yourself that's a screw right here. And so this I'm going to call the pivot point right here. And again, I could kind of twist this thing about that pivot point. If I was perfect, I could hold it perfectly still. And we see this thing rotates about there. So right now, you could think of there's two pieces of brass, and the weights of these two pieces of brass are exerting torques about the pivot point. What do I mean by that? The weight of this piece of brass is pulling down right here. So notice it's some distance from the pivot point, and that's going to cause a torque. A torque is a force that's going to tend to cause a rotation. Now there's this other piece of brass, nearly identical. So they have the same mass. And then the idea here is this one is a different distance from the pivot point. So even though they exert the same amount of force on this thing, notice I'm trying to hold it still here, but it's very difficult. And that's because this force, which is the same size as that force, exerts more torque. Again, this is a larger torque than that. And we see that because when I try to hold it still, it rotates. This force wins, even though it's the same size. So torque has to do with the distance from the pivot point. It also has to do with angles. Look at this. When I hold this thing vertically, if I can get out of the way there, if I hold it vertically, you notice it's not trying to rotate. Whereas if I hold it horizontally, it's almost impossible for me to stop it. So the idea here is the angle may also affect the amount of torque. In this case, I'm barely holding this thing at all. There's almost no rotation at all. It's basically staying at rest, and I'm barely gripping this thing. Whereas even when I grip this thing tremendously here, you can see I'm like mutilating my fingers. I could almost barely keep it from twisting. Clearly, there's much more torque when this thing is horizontal than when it's vertical. Okay, so what are the factors that affect torque? Distance, the amount of force, and the angle. All right, so let's go in and look at some pictures now and see if this makes some sense. The idea here is the angle between the force and this line here. We'll discuss these lines in a minute. And this is generally called, R is the vector from the pivot point to the point where the force is applied. This is probably the most important definition. Put an underline on that one. Okay, so you're going to hear me say the R vector. This is the classic definition of torque right here, R cross F. Well, we've done chapters and chapters understanding force. I want to be very clear here. You don't get to choose what you want to do for this R vector. R vector is chosen for you in this special definition here. There's a pivot point. R vector is from that pivot point to the point where the force is applied. Notice the arrowhead here, right? It's from the pivot to where the force is applied. This is a big deal. Previously in our FBDs, we used to draw things as a dot and just draw all the forces acting on them, right? When we used to do problems with FBDs, we just draw a dot. Now we can't do that anymore. A free body diagram, we need to visualize the entire rod that has a force acting on it, or the entire plate or whatever. So our FBDs need to improve. We're no longer just going to do a dot. We need to show where the force is applied, because we need that to understand this R vector. I think that's enough on that. But any questions so far?
So in your demonstration, the force that was acting on it was mg, right?
In this case, yes.
Okay.
And I guess we should be careful. The force magnitude was mg. The force vector would be mg negative j hat.
Mm-hmm.
Yep.
Okay. And so then the pivot point is the axis where it's rotating.
Yeah. You want me to draw it up here just so we could see it on the whiteboard?
Sure.
Why not, right? And then the definitions will probably make more sense. Hopefully I remember to tell the other class that. All right, so the idea was we had a pivot point right here. It was right in the middle of this rod. And I'll color code. Maybe that's not quite in the middle. So let me make this rod a little bit longer. Whatever, good enough. So let's say we had a point mass right here. mg is the magnitude of it. This is our pivot point. And then over here, maybe only halfway out, let's say, it doesn't matter. We had the same size mg. Now, just so we're clear, let's put on a coordinate system here. Okay, so we could say that the origin of this is right at the pivot point. That's a convenient location for this coordinate system for discussing this. And I'm just going to kind of eyeball this. Again, I'm looking at this situation right here where you have one mass far from the pivot and one mass close to the pivot. It's not to scale, but it's close. All right. And let's just say this is about, I don't know, 30 centimeters long. So let's say this whole thing is 15 centimeters. So over here, this distance, notice I said distance, is 15 centimeters. And let's just say, to make it easy, let's just say this one is 8 centimeters. I know it's not exactly halfway, but it's approximate, okay? Doesn't matter. So in this case, for example, torque 1 would equal radius 1 cross force 1. In this case, radius 1 would be what? You want to try it, Esteban? You're the one that spoke up. You don't have to.
So I'm thinking 15.
Okay. I'm assuming this is number 1. Sorry.
Okay.
So let's call this one number 1.
Okay. So I guess.
Sorry about that.
Yeah. So it's a vector. So yeah, it has to be 8. Right, 8, and then times mg.
8. You said vector.
Yeah. So
that's
okay. So it's going backwards. So it's negative 8.
No. 8 centimeters. No. J hat. K hat.
Oh, it's a I hat.
I hat. So that's the R vector for this case.
Right.
Now, what's the force?
It's mg and negative j.
Yeah, that's what I'm talking about. Can I write negative mg j hat? Is that okay?
Yeah.
So that would be how you could figure this out. Mm-hmm. This is not times. How do you say this?
That's cross.
Cross. So we'd say it's R cross F. Those cross products you did in chapter 3 are finally showing up again. Right. This is why we spent the effort on them. And so how would you solve this?
Well, it'd be IJK, right?
Wheel of pain.
Yeah.
So now we see I goes to J, goes to K, goes to I. So you tell me, let's pretend that mg is 7 newtons, okay?
Okay.
I don't know why, but who cares? Let's just say that's 7 newtons. I just picked a number. Okay. So what would the torque be then in this case?
So you have negative 56 K newtons.
Negative 56 what?
Newtons times centimeters K.
Newton times centimeters. And then I'll just say I cross J, which Esteban already did that step. He said I goes to J goes to positive K hat. That would be a torque. Got it?
Now, does the radius is also a vector. So what on the other side would it be a negative 15?
Yeah. So
Okay.
let's do torque 2. So this would be torque 1. And then so I'm going to write that up here so I don't forget it. Is that okay?
Yeah.
So I get negative 56 Newton centimeters K hat. Now wait a minute. Let's think about this before we do the other one. What the heck does K hat torque mean? Think about this. If I push on, if this red one's pulling down here and this is the pivot point, would this tend to rotate clockwise or counterclockwise?
Counterclockwise.
It would tend to go just this one. If I'm forgetting about this one, if it's only this one, this would tend to rotate it which way?
It would tend to go down, so clockwise.
Notice that's the same thing as sticking my thumb along that axis, and notice my fingers curl. So this torque is talking about the axis of the torque. So this is equivalent to saying
that's going negative K 56 newtons per centimeter.
Clockwise, I think, right? Isn't that what I don't know what that looks like on Zoom because I have no idea. Hopefully, is that clockwise to you guys?
Yeah.
Okay. So is that good on that, Esteban?
Yeah.
So notice negative K hat here implies stick your thumb of your right hand in the negative K hat. How do I know which direction is K hat? Well, I know the wheel of pain must be valid. So if this is I hat and this is J hat, K hat would have to be out of the page. So negative K hat is into the page. Makes sense. It's at least self-consistent. So far, so good on that, everybody? That's a lot of weird stuff. Any questions about the I hat, J cat, whatever? Any questions about the I hat, J hat, K hat, or how I know to do this, or any questions about that from anyone before we do the other torque?
I had a question about the R vector.
Yeah.
Why isn't it negative J hat? Because doesn't it start from the mass to the pivot point?
It's so think about this right here. This is a good question. It's sneaky. Here's the deal. Look, imagine this is our system, right? Okay, so here's the pivot point. We want to go from the pivot point to the point where the force is applied to the rod. This piece of brass applies that weight effectively at its center of mass, which is right in the middle. So effectively, that red force is applied right here at the center of it. So that's why we go from here to there. We don't go from here to the tip. Is that what you're asking or not?
Oh, okay. I think I just had that backwards because I was thinking that we start from where the force is applied and then go to the center.
No, it's from pivot to point where force is applied. From the pivot to the point where the force is applied. Yeah, I'm going to say that about 1 billion times today. So we'll get that locked in by the end of today. Good enough for now?
Yeah, thank you.
All right. Now, since you were crazy enough to speak up, let's have you try the other way. Is that cool? And it's okay to screw up. Just remember that this over here, this mg, we're going to assume is 7 newtons. So now I want to figure out torque 2, and I'm going to write it a little bit further this way. That's going to be radius vector 2 from the pivot to where force 2 is applied, and force 2 vector. So in this case, was that Dom?
Yeah, it was.
What do you think I should use for radius 2 vector?
So that should be -15 j hat.
Negative 15 centimeters. Which hat?
I hat.
I hat, right? It's to the left. So negative I hat means to the left. Cross product with F2, what's the force 2?
The same -7 in the j hat.
Yep.
7n.
Yep, 7 newtons J hat. And so now notice we got a negative times a negative. The torque is going to be 7 times 15 is what, 105? 70 plus 35? The minus signs cancel. I still get I hat cross J hat, but now there's no minus sign. So notice I get a positive torque, right? Positive K hat. And lo and behold, this matches up with what we assume from just looking at the damn thing. This should exert more torque than that because it's farther from the pivot. Okay, so now if I try to hold this one, it's very difficult. Why is there no torque at all when I hold it this way? What changes when I hold it this way? Do the force vectors change?
The force
Well,
vector.
Does this still exert a force of 7 newtons in the negative J hat?
Yes.
Yes. How about this one?
Yes.
So what would be different in the torque calculations?
The distance in the I hat direction.
Would become distance in the
J hat direction.
What's J hat cross J hat?
0.
What's the torque?
0.
No torque. This is consistent. What do you think about that? Any questions?
If you had like the heavier one on
Uh-huh.
top, wouldn't there still be torque?
No,
Oh, okay.
but it's hard to handle. Why is this difficult to keep this straight up?
Because that distance is a lot farther, so it takes like less to make it move.
It's because you can't be perfect, right? If you could hold it perfectly straight up, and I'm almost doing it, there's almost no torque. So it's actually pretty easy to balance compared to the horizontal case, right? I don't know if you could tell this, but I could pretty much do this. The problem is any slight misalignment, this thing's going to try to go. So it's unstable. If you think about chapter 8, this is an unstable equilibrium point. Any small deviation from vertical and the thing goes. This is stable. Any small deviation, it wants to come back. So we see that here's an unstable equilibrium and here's a stable equilibrium. They both have no torque, but one is easier to hold than the other because of real life. It's impossible to be perfect. Is that good on that?
Yes.
Pretty wild stuff, right? It all comes together.
So could we just use RF sine theta? Would that work too?
And so now we get to what if it's at an angle? I don't want to do that all the time. Do you? So there are shortcuts and tricks, and that's what Esteban brings up. Here are the 4 ways to do it. There are several different ways to do torque. We did the unit vectors in the wheel of pain because that always works. If you get stumped or if you have to take a higher level class like statics, you basically have to do problems this way once you get to real life in 3 dimensions. Let's just face it. So this is a good method to learn because it works for everybody. Imagine how easy this would be in Python. You could just get ball.pos minus pivot.pos, punch in a force, negative mg in the j hat, 0 in the right. So this is also useful for coding. Anyways, you could use this method that Esteban just said, right? Notice something is slightly wrong here. What's wrong with my equation here?
You forgot your vector.
Mm-hmm. So notice, how did I fix that up over here?
You put counterclockwise
I
direction?
listed the direction. How do we get that direction? If I want to know the direction of a cross product, does anyone know how you could get the direction of a cross product without doing the I hat, J hat?
The right-handed rule?
Right hand rule. It's somewhere down here. There it is. So somewhere on your page down at the bottom, this shows you how to do the right hand rule. So you've got this on your paper. I'm going to show you on the whiteboard. All right. And if you are able to do this, I know it seems stupid, but just get your right hand out and let's get to work, people. So try and do exactly what I do. All right. Line up your hand with the computer monitor. Start at the pivot. Go from the pivot to the point where the first force is applied. Let's pick this red one, or F1 as we called it. So I line up the fingers of my right hand with that. Now notice, before I go on, there are 4 different ways I can line it up. Here's 1, here's 2, 3, and 4. Those are all possible ways to line up your right hand. So this is the practical way to do this. Try one of them. I'm going to choose this one. Now, curl the fingers of your right hand. Do they point in the same direction as the red arrow? What do you think? Just say yes or no.
Nope.
No. How about now?
Still no.
No. How about yes? Agreed? So you just mess around with this, and in practice, if you're doing problems on paper, you could turn the paper and keep your hand the same way. So, right, you turn the paper underneath your hand until your fingers line up with the arrow, or just do this. So now this, what direction is the torque? It's in the direction of my thumb. So R goes to F, goes to torque. R cross F means R goes to F, goes to into the page. That's how I got this negative K hat. How about this one? R goes to F, out of the page, positive K hat. Going into this one, R goes to F, so just try to line up your right hand with that. And I think, don't you get a direction out of the page for this image that is at the top right corner of page 69? Try it. Out of the page is counterclockwise. Counterclockwise is K hat. So you could have also written K hat here. And notice I wrote K hat on one of the pictures, counterclockwise. So those are the 2 kind of standard ways we would write that. Esteban, does that address your question of how could you use this?
Could we just go really quick over how we would apply it to the what we already have on the board, just to get like a little concept?
Okay, so let's do torque 1 again. Okay, is that cool?
Yeah, just real quick, just so
torque 1, it should equal R1 F1 sine theta 1, and then it's negative K hat from right hand rule. Are you okay with the right hand rule part? Sorry, I spent all my time on that.
Yeah. So yeah.
Okay, so this is the vector and there's the vector. So now what would I plug in for R1?
So 8. So 8 centimeters.
Do I need the I hat or not?
No,
because it's a magnitude. We took care of that vector crap.
Yeah.
What do I do for force 1?
It had 7 newtons.
And what do I do for sine theta 1?
That's what I'm trying to figure out.
Okay. It's the angle between R. So if this is R1, that's R1. This is F1. What is the angle between those two?
So just 90 degrees.
In this case, it's 90 degrees. Now, wait, which one should it be? Should it be that one or this one?
The first one?
The first one is correct. The second one is also correct. This is one of the few times in physics you can screw up your angle and get the answer right. Either one would work. Why? Because sine of theta is equal to sine of 180 minus theta. This is true. And so it turns out either one will work. Supplementary angles have same sign. Cool?
So if the angle wasn't 90 degrees, it'll still work.
It would still work, and either one would still work. So there we go. And notice, what's sine of 90?
Just 1.
And so we get 1 for this. We get 56 Newton centimeters.
And then we get the negative K.
Yeah. Now, here's a weird thing about these units. What's a Newton times a meter? What's the unit?
Normally a joule.
A joule. So, however, to clarify we're doing a torque problem, we don't write joules here. If anyone has ever heard of a torque wrench, usually you measure torque wrench in foot-pounds or Newton meters, or in this case, you could even do Newton centimeters if you wanted fine resolution on a torque wrench. So what is a torque wrench? If you've ever heard of this, it's just a wrench that's going to literally have a gauge on it telling you how many Newton meters or foot-pounds of torque you use. Now, why we don't say meter newtons, but we do say foot-pounds is beyond me. But foot-pounds is a common unit for torque, but drives me crazy because it's not metric. So we're not going to use that. We're going to use Newton meters, even though it should be meter newtons. And we don't say joules, even though it is technically a joule. Cool?
Is it just Americans that use foot-pounds?
To be honest, that is not my expertise, but most countries in the world use metric because it's just easier to divide stuff by tens. So, And so as a scientist, you'll get used to that. There's Angel. He's bringing that up. Oh, so that's cool. Yeah, because you know the work is done, right? There you go. So, very cool. Yeah. Okay, so let's, I think that's good on that one, right, Esteban? Sorry about that. Trying to remember what we were doing.
Yes, we're good.
So now what do you do if it's at some crappy angle? This is what I'm saying. You could use this angle or that angle because it'll always work for sine theta. This wouldn't work for a dot product, but it does work for a cross product, it turns out. Cool? Now, at this point, we could totally start doing problems because we've got 2 different ways. However, it is worth it to learn 2 more of these. Again, notice, do you see that there's no vector on this side or that side? You have to do the right-hand rule. Now, you may say, I'd rather just use the unit vectors. I'm telling you, there are certain problems where number 1 is the best. There are certain problems where number 2 is the best, and certain problems where 3 or 4 is the best way to do it. So I'm not trying to gaslight you here. There are times when each of these methods is the best. If you read the internet and try and understand other people's work, there are times people will use all 4 of these. And if you don't know all 4, you're just kind of at a disadvantage. Some problems take much longer this way than this way. Some problems are much easier to understand physically this way. So let's understand 3 and 4. Look at problem 3 here. All right, so notice here, this dotted line that this line right here that I drew an arrow to, that is a special line. It's called the line of action. It's a special term. Line of action is a line drawn through the force that extends to infinity in both directions. It's an infinitely long line. R perpendicular is a special part of the R vector. Give me just a second, circling it here. R perpendicular has a special name. It's called the lever arm. It's shown right there. It's perpendicular to the line of action. That's why we call it R perp. You're going to hear me call it R perp a lot, for R perpendicular. What's R perp? What's our lever arm in this problem? Now notice in this case, if this angle right here is theta, this angle right here is theta, if this vector right here is R, give me a second. If that is R, notice R perpendicular happens to be R sine theta. So what you're doing here, R perpendicular, is simply grouping the R and the sine theta together in a special way that has physical meaning. It's the distance from the pivot to the line of action, not where the force is applied, to the line of action. Okay? It may seem silly, but there are times this is exceedingly useful and reduces calculations massively. All right? Any questions about that right now? We haven't done any examples yet. All right. Take a guess what F perp does. What do you think? What do you think this F perp does in terms of this equation?
So perpendicular from F to, what would you call the line after the radius?
We could just call it the R vector.
Oh, okay. So perpendicular from F to the R vector?
Yeah, exactly. Which effectively, mathematically, is grouping the sine theta and the force together. So let's go look at that in the picture down here. You just take the component of the force perpendicular. All right? And so hopefully that picture makes sense. The idea is, well, the force that's parallel to this thing, think about this. Let's just say this is R hat, okay? Actually, I'm going to change this. Let's call this parallel hat. And I'm going to call this direction perpendicular hat, okay? Notice this is the force that's parallel. If we did the cross product, this is going to be faster on the whiteboard. Sorry. Going to the whiteboard. Just so much faster for me. Okay, imagine you have some random pivot point. You have an R vector. You've got a force here at some direction here. Oh, actually, let's color that some other color just so we can see it better. There's our force vector. Now, normally we draw our force components like this, right? However, I don't want to do that anymore because that makes it look like the force is being applied over here. So I'm going to grab that vector and slide it over so that its tail appears just like we did in the coding last week when we showed the components acting at the ball. Remember that? So in this case, I'll call this force parallel in the, I'll call it parallel hat. That looks kind of weird, but whatever. This is force perpendicular in the perpendicular hat. Again, it looks kind of weird, but so what? If we do the full torque equation here, torque is equal to R cross the force. Let me write it a little bit lower so I have room. Sorry. So it's R, the radius vector, from the pivot to the point where the force is applied, crossed with the force. Force perpendicular in the perpendicular hat plus force parallel in the parallel hat. Which term will not survive the cross product?
Parallel.
Parallel, right? Because it's parallel to R vector. So R vector crossed with something parallel to the R vector drops out. And the only term that survives is R times F perpendicular. And notice the cross product would give us R goes to F, goes to out of the page, which means it twists this way. So far, so good. All right. Now, let's go back in there. There's a bunch of different things here. This is a common relationship. We're going to see this a lot in this chapter. So you got to memorize this stuff. Okay. Here's one thing. If the line of action goes through the pivot point, it causes no torque. That's huge. That will save you time. It's not just forces that touch the pivot point. It's lines of action that touch the pivot point cause no torque. Okay, exactly for the reasons we just discussed. If the line of action goes through the pivot point, if the line of action for a force goes through the pivot point, there would be no perpendicular hat component. All right, this is just for simplifying math. Sine of 90, right? Think about a right triangle here. If this is theta and this is 90 minus theta, sine and cosine flip-flop. So if you have sine of 90 minus theta, that's the same thing as cosine of theta, right? This is cosine of theta. Well, isn't that also sine of 90 minus theta? It is. So that's where these come. And then this is one, I just did the math, just know this. Sine of 180 minus theta, sine of theta, same thing. We already know this because we know F equals ma. We know torque is the equivalent of force. I is the equivalent of mass. Alpha is the equivalent of acceleration. Torque is a vector. Don't forget that. In standard math notation, we're going to say k hat and negative k hat are counterclockwise and clockwise. However, watch out for physics problems reassigning, because if everything goes clockwise, why don't we just make clockwise positive? And I can't stress this enough. It's from the pivot to the point where the force is applied. We know your right-hand rule. And notice, this is something I already said. It's useful to put the components at the tail of the force for these types of problems. Instead of doing both the components and making a triangle out of it, we don't want to do that anymore. You want both components. You want to put the tail of these there. And when you do that, notice you could split a force into components and do lever arms, etc. Basically, you're doing a cross product without having to do a determinant in a 3D matrix. All right. I got a question for you. So I want you to think about this. I've got a door back here. I don't know if you can see this. So I'm going to go over to this door and think about the torques here. I don't think these headphones will reach. But yeah, you could, oh, you know what? This is kind of difficult. I'm going to try it anyways. This is usually what I do in the lecture hall, so my brain's still in person. What I'm going to do is I'm going to show you some bad ideas and good ideas for opening doors that you already know, but I want you to think about why they're bad from the torque equation perspective, all right? So I'll babble loudly. I don't know if you'll hear me or not. All right. So here's the door, right? This is a bad way to open a door, right? Because my force is going right here. The pivot point are these hinges, right? So if I push this way, the axis of rotation is right there. The line of action goes through the axis of rotation, all right? And then here's a bad idea for shutting a door. I could try to push it shut from right here. It's a little difficult to shut the door from right here. Why does it take so much more force? I don't know if you could hear that at all, but it's dumb to close a door by pushing on it near the hinges. Why is that dumb from a torque equation perspective? What is bad idea about that?
Because the R hat is really small.
Yeah, the R vector is really small. So if you want to close the door, you need a certain amount of torque. Well, if you have a very small value for R, you're going to need a huge value for F. Similarly, right, you don't try to push towards the hinges of the door to close it. That's exerting massive forces on the door, and it's very difficult to shut the door. And then if you slip at all, it's going to slam and smash your fingers and cut them off. So we don't want that. So in general, the angle matters, the distance from the pivot matters, and of course, the amount of force matters in a torque. That's what that's supposed to kind of point out. Now, you can actually open and close doors that way. It just takes a tremendous amount of force if you use those other weird ones. All right.
And that's how kind of levers work, right?
A lever, so, yeah. Thus the term lever arm.
Yeah. Okay.
Mm-hmm. Why do you? Yeah. So like this. If you're trying to tighten a bolt, right? It's a lot easier to tighten the bolt by gripping this piece of brass than it is by this one. Now, there may be times you have to do this because your hand can't fit in a small space or something, but it's very difficult to exert torque if you're close to the axis. So it's hard to, or now, how does a screw work, right? If you look here, there's the screwdriver in here. Sorry if you can't see. You're exerting a torque. The pivot point is essentially the center of the screw right there. And so when you put this on here, the two tips of the screwdriver are slightly displaced from the center of the axis of rotation. So this point and that point, the two ends of the screwdriver can exert a torque. Now, if you've ever noticed, if a screw is on there really tight, it's very difficult to do it because look, you're trying to twist this. Your hand is exceedingly close to the axis of rotation. So it's very difficult to tighten and loosen some different screws. It depends. So yeah, now I don't know, there's trade-offs, right? You could make a jumbo handle and then it's easier to grip the handle, but then at some point the handle's too big to fit in your hand comfortably. And so there's a trade-off between ergonomics of torque and being able to grip something comfortably and twist it versus you want to have a large radius, right? So in theory, you could say, isn't the ideal screwdriver something like this, where you just take a giant plate like this and rotate it? And imagine how easy it would be to get torque. So if you could somehow couple that to the screwdriver, sure. But if from practical standpoint, that's pretty obnoxious to work on a day-to-day basis. So, but yeah, is that good on that? Whatever that question was?
Yeah, that's very interesting.
Mm-hmm.
So I guess it's basically the ratio between the handle and the metal part of the screwdriver is really what you're
for a
focusing
screw, yeah.
Mm-hmm.
Now, what about a socket? A socket's got that right angle built in. I don't have a socket here with me, but right, you take a socket, you put a socket on there, and then there's a handle sticking out. You don't get enough torque, you put a pipe on the end of the socket, you increase your lever arm, it's easy.
Yeah.
And then you break something. All right. Angel probably knows a lot more about that, right? Sounds like you work on stuff.
Yeah, I took a couple classes on working on cars in high school.
Cool. So I don't know anything about it really. I mean, just the other day I lost my socket wrench inside my car changing the battery. So it's still in there, I hope, maybe. I don't know. Yeah, so I'm not the guy to talk to about automotive repair. If the thing runs, that's good enough for me. All right, so let's get back into the core content here. All right. We already did an example like this one, but maybe let's just look at the solution and make sure this looks good. So, okay, actually, let's just look at the solution for 10.36. So you've got a force and we want to figure out the R vector. Maybe you could tell me that before we look at the solution. How would I get the R vector for this particular case? So take a second to look at that. Sorry, I'll give you a second. And this is 10.36 at the top of page 70. Yes. Anybody who wants to. Take a guess at it. It's okay if you're wrong.
So I guess it depends on which. So if we were doing cross product, I'll just do.
Over here, I just want the R vector, not the torque.
Oh, okay. So it's just 1.5 meters. Right?
Nope.
Oh, because it's an angle.
Yeah, so I want the R vector just like I want it in Cartesian form.
Yeah.
You see where I'm going with that?
Do we have theta? Yeah, 30 degrees. Yeah. So just our cosine and our sine.
So 1.5 is the length. I'll put the meters way out here at the end and put some parentheses now so I don't forget. 1.5, what do you say? What's the x component? Is it 1.5 sine or cosine?
Maybe sine.
Yeah, so that's sine 30. Sorry, I'm getting sloppy here. Forgetting sig figs. Positive or negative in this case?
Positive.
Positive I hat. And then the next one would be 1.5 cos 30 j hat, right? So this side is cosine because the angle's to the vertical. All right. So at that point, we should be able to just plug in and do the wheel of pain, right? You could do this some other way. And so notice, I don't know if this is in your book or not, but we could also figure it out by determining lever arms for each component. So let's go look at this one and see how this works out. Maybe I've got the solution 10.36. And Zoom is blocking everything here. All right. So there it is. So there's the R vector. You just get the L sine theta. Oh, shouldn't that be cosine? Cut and paste error there. So what is this? 10.36. Sorry about that. I'm sure that makes sense what to do there. Okay, so now here's the force. Here's the wheel of pain crap, and you get it all worked out. Check this direction with the right-hand rule. Does that make sense? To check this with the right-hand rule, take the fingers of your right hand and line them up with the R vector. Curl the tips of your finger to the F vector. And notice your hand should point, or your thumb should point into the page, which corresponds to negative K hat. Again, R goes to F, thumb points into the page using your right hand, and you get that thing into the page. So I'm just going to pause. Any questions on 10.36b? That. Okay. Here's another way to do it with lever arms. And this is going to look a little bit weird. So I'm going to just show you because this is better than the picture I can draw on the board right now. Take a second to kind of read this. The X component of the force is 3. The Y component of the force, magnitude, is 4, right? It's negative 4 in the J hat. The magnitude of the Y component is just plain old 4. This is the lever arm, or R perp, for F subscript Y. That's the distance from the pivot point to the line of action for the vertical component. Similarly, this is the perpendicular distance, the lever arm, R perp, for the X component. Notice the line of action here for the X component is horizontal. And we're going from the pivot to the line of action. So that's how lever arms work. And notice when you do this, we say, okay, R perpendicular for force 1, there it is. I got the magnitude. Then I do the right-hand rule. From here to that line of action, you could curl your fingers and see, okay, that looks like a negative K hat. You could do the same thing here. From this point to there, the force is going down. That force component's going down. I also get a negative K hat. So both of the, now, if you didn't like that, you could just go from here up to the original point where the force is applied, and it still works the same way. If you go from the pivot point to where the force components are applied, you get the same result. Lever arms look more complicated, but imagine you get weird forces. It starts to become very systematic to split them into components. Only some of the components will matter, and then you only have to do torque calculations for the components that matter, and you save yourself some time. Oh, shoot. Sorry about that. Any questions about this R perpendicular crap? Is that making any sense? You get the same answer.
Yeah, at first I was confused because I was like, how is it that? But then I realized that the force gets separated into two vectors, and that's why they're both perpendicular. Yeah, so
yes,
it
exactly.
makes sense afterwards.
And so if you split things up into good components, it's actually easier to find lever arms sometimes than to get angles. That's the trick here, is this is the original force. Notice the angle theta is not the angle that we need to use in RF sine theta. It's a decoy. It's sine of angle between. I'll call this theta RF, the angle between R and F. And if you look in this picture, the angle between the radius vector from the pivot to the point where the force is applied is not theta. And so students get lazy and tired, overworked, and they just shove in, just stick in theta in this equation and think I'll get it right. So by forcing yourself to do lever arms, you sometimes make fewer mistakes. Believe it or not, it looks harder at first, but then you do fewer mistakes. That's the advantage. All right. Is it good for every problem? No. It's good for some problems. Okay. So let's go back to here. In this one forces you to remember some of these symbols. What does an X mean like this? What do you think I mean by that X?
Into the page.
Into the page. And then this dot over here is out. So watch out for that. And so you could see, notice I'm drawing a coordinate system here. It's starting to become very crucial that you always draw a coordinate system. And notice now I'm including the Z hat all the time. So it's always, always, always crucial to check before you do any work, does your coordinate system obey the wheel of pain? Is your coordinate system right-handed? Does X go to Y, go to Z when you do the right hand rule? So you can see beyond the screen. I just want to be clear. Every time you draw a coordinate system, anytime for the rest of your life now, draw an X and a Y and then just quickly double check. X goes to Y, goes to Z, is out of the page. What if you did it this way, where X is out of the page and Y is to the left, then Z is up? Those are the two most common. Usually we say X, Y, Z or X, Y, Z. Always double check that your coordinate system is right-handed before you waste time using the wheel of pain. Simple check. It's worth it. It's like checking the units on your answers. So I'm going to let you guys try these ones out at home. I hope those are in the solution. Let me make sure. Yeah, so I gave you the answers there. Notice some of them were 0 and some of them were not 0. Let's maybe look at those zeros. These last two are 0. Can someone tell me a good reason why we can say the torque in case 5 is 0?
Line of action runs through the pivot point.
I like the way you said that. How about for case 6? Somebody else?
It runs parallel to the pivot point?
Runs through the pivot point. Line of action runs through the pivot point, because parallel to the pivot point is confusing. That would be, well, like, let's say that's the pivot point. What if you applied a force kind of out of the page like this, and the line of action runs like this? That's parallel to the pivot point, right? But that causes a torque. So you have to say line of action runs through the pivot. So that if you see, sometimes people say in case 5, the force is applied at the pivot point, so the R vector is 0. That's a true statement. That's a good way to say it. However, I think it's stronger to say line of action runs through the pivot. Cool? All right. Here's an example you could do at home. It's pretty simple. You should probably do this one. And so you can see that there's a pivot point right at the center. The rod has negligible mass and these forces are applied to it. If you're wondering what it means to have negligible mass, it just means the mass of the rod is negligible, the weight of it, compared to all those huge forces, right? So that is effectively like this. We're going to take these off of here and have just the rod. So right now, what I'm saying is you could push in different spots at different spots with different forces, different angles, and you could see which of these cause torques which way, and that'll just be a way to check what we've already done today. We've already basically done that example, but with some weights. So this is a variation on that one, okay? So I'll definitely do this one, even if it's not in the required problems, because this will check before you get to the hard problems. All right. And so now, I know. Let me just check something. Our quiz starts at 1:45. So what I'm going to try and do is go all the way up to say 1:30 before we take a break, because I just want to get as much as we can done. So, but I will give you a 15-minute break today. All right, before the quiz starts, or the group activity, or whatever the heck it's called. So if you are really tired and need to go grab a drink of water, let's do a micro break right now. I need to fill up my cup of water. Just get some water, go pee, and then let's get right back on it. So like a 2-minute break, okay? All right. Let me just eat a couple golden grams and I'm ready to go here. Okay, so I was probably just going to start back up right now, or maybe I'll wait. I'll wait 1 more minute and then we'll just go. I don't want to waste too much time on a break because we're going to take one later. Maybe I'll only do a 10-minute later. Just want to make sure anybody that needed to could use the bathroom or get some water. Okay, any questions before we get back into it and try and do a couple of real problems? I'm going to go for it. And sorry, it's a little weird today. Okay. Let's take a look at this one. I'm going to draw it up. You could do your picture and let's just start working through it. Looks about right. Oh, okay. So at the instant shown, 3 forces act on the rod. There's the rod's weight. Where does the rod's weight act on the rod?
I would say at the tip, at the end point.
Where, generally speaking, where is the mass effectively?
Oh, a center of mass.
That's why we learned center of mass. So that's where mg gets drawn, right? mg is at the center of mass. Now, there's this force downwards. There's this force up at this angle. Okay. And it says there's a reaction force at the pivot. Okay. What does that mean? Essentially, it's a bit of a misnomer, but the idea is there's a force at the pivot point. Now, I don't know if you could tell, but this force is trying to pull it to the right. Which way do you think the pivot point pulls on it?
To the left.
Probably to the left. So there's probably some component this way. We could call it Rx. That's just the terminology we're going to use. And there's probably some component upwards, Ry. Now, you might not like drawing it this way. Sometimes people actually draw it like this. They don't draw the Rx that way. They say, look, Rx is going to the right and Ry always goes up, but we expect a negative number for that. So anyways, those are the forces that act on this. Okay. So if I draw this here, there's the weight right here. And then let's just say for right now, there's an Ry and an Rx. Immediately, oh, whoops, shoot, I forgot to stop share. Hold on, sorry. There we go. Okay, so we've got this picture, and this was problem 10 point something. 39. Okay. So the idea here is which 2 forces don't contribute to the torque?
So Rx.
Rx and
Ry.
Yeah, because line of action through pivot. So if I want to get the torque and the angular acceleration, I know the sum of torques equals I alpha, right? This is my pivot point, just making that clear. Let's do the torques one at a time. So we're going to have the torque due to F plus the torque due to mg equals I alpha. Now I should be careful here. What did I screw up?
Is alpha a vector?
Yeah. Assuming we keep the pivot point, as long as we rotate in a single plane, we could assume the angular acceleration is a vector. It'll act just like it. All right. So now, in this case, how do I get the torque due to F? Give me any way you want. By the way, class, at this point, I could give a rat's ass if Esteban's the only one contributing. I think it helps you when Esteban and I have a conversation. And because I know not everybody has good internet and this and that. Am I wrong in that statement? I don't want you to feel like I'm ignoring you, class. I don't want you to feel like I'm focusing on Esteban, but like does that help you or not? Just
This is like
put
the
it.
backbone of my understanding.
Yeah. So the back and forth between Esteban and I is helping everyone. Hopefully.
Yes.
Yeah.
Okay. All right. All right.
Yeah.
And obviously, you guys are welcome to contribute too. I know like Dom does and Alan does sometimes. And yeah. So anytime if you, just contribute or just lay back and listen to our conversation, whatever works for you. All right. Whoops. Not sure.
I can be quiet too if you want me to.
I try to keep an eye on it, Esteban. So I try to be
Okay.
like, if I really want somebody else to contribute, you know what I say, right? I'm like,
Yeah.
okay, somebody other than Esteban. All right.
Okay.
Yeah. So you're doing great. All right, Esteban, you spoke up. Let's just roll with this one and rock it out. Okay. How would you approach getting the torque due to force F?
Well, to separate force into its vectors or to X components, X and Y components. So
it sounds
Yeah.
like you're doing method 4. So what's this component? Is it F cosine or F sine?
that would be F sine.
Yes. It feels uncomfortable writing it because it's a cosine usually, but yes. And then this component up here is F
Cosine.
cosine theta. Got it. And so then what is the torque due to F?
So the F sine theta is running through the pivot point, so that one cancels out. So you only have F cosine theta.
Okay.
So it'd be R times F cosine theta.
What is R in this problem?
And this problem, do we have the length of the rod?
L. L is the length
Okay.
of the rod.
So it'll be It'll be
Okay.
LF cosine theta.
L F cosine theta is almost correct.
Okay.
What did you forget that I forgot earlier?
Vector.
Vector. So tell me which way.
It would be in the
Should we
J
draw-
hat.
Let's draw a
Yeah.
coordinate system first. This
Okay.
is, I'm assuming this is I hat. This is J hat, right?
Mm-hmm.
So if this is I hat and J hat, which way is K hat?
K hat would be out of the page.
I goes to J, goes down out of the page. So that's K hat. Okay. And so what is the torque direction for this one?
So it'd be K hat.
Let's see. Yes. Right? Oh, sorry.
Yeah.
And so again, K hat means the axis of the torque. So imagine you bolt your thumb to here and you notice that force tends to twist it upwards. So this force is trying to twist it. What did we say? K hat?
Mm-hmm.
I totally forgot. All right. How about MG? Somebody else. Let's let somebody else try that now that Esteban did one. Anybody that wants to.
Could it be L times negative mg?
Okay.
K hat?
So let's see. We want to do okay, not quite, but very close. What's the distance?
Would it be L over 2?
L over 2 mg, and then it's in the negative K hat. So I'm like you said, you're right. That's good. Cool. So we see that not everyone has the same lever arm or the same angle or even an angle at all. This one, well, this one had a 90 degree in it. You could have said it's L/2 mg sine 90. That's another way you could have done it. Or you just say, well, look, it's already perpendicular, so the lever arm is just L/2. Okay, what's the moment of inertia? Somebody else. Take a guess.
Is it 1/3 ml squared?
Yeah. How'd you know it wasn't 1/12?
It was at the end.
The pivot's at the end of the rod. So that's where we use that. 1/3 ml squared alpha. Now, I just want to point out, you could actually drop the k-hats. So a lot of times what we do is we just drop the k-hats here, keep the minus signs, drop the vector, and we know that if I get a positive number, it's rotating this way. If I get a negative number, it's rotating that way. At this point, you could plug in any numbers you want and solve for alpha. We got it. What do you think? We can now handle, this is basically like doing FBDs and getting acceleration, then you plug it into kinematics. What we've now done is a better FBD where we don't just show the forces, but also the points where they are applied. And then we can get the angular acceleration. Beautiful. Tears of joy. Okay, so let's take a look at the solution, see if there's anything good in there. Okay, there's that one. Ooh, look what I did here. So see how I drew my coordinate system? So I said, this way is a positive torque. Oh, look what I did. So I said, well, if this angle up here is theta, that means this angle down here is 90 minus theta. But I know from trig identity, sine of 90 minus theta is cosine theta. I get the same junk. And notice I said there's an implied k-hat on all terms. So you get some big ugly mess. It's not that bad. It's just ugly. Beautiful, beautiful, beautiful. All right, let's take a look at another one, right? Or any questions before we go on any of that?
You did mention that the question mentions that's uniform density, and then it's also that's frictionless. Are we going to have problems where it's on uniform density and friction added to it?
You could easily do that. I mean, imagine a final exam question where I say, do the same exact problem, except then I say the rod is non-uniform. So what do you have to do? What would be different?
Find the center of mass.
How would that affect the problem?
Well,
if you find the center of mass, what would be different about this picture?
Where mg is?
Mg would be located at the new center mass. Would anything else change?
No.
Yes, the moment of inertia would be different because it's... All right. Now, to be honest, what I would usually do is I know people would fuck that up all the time. So what a lot of times what I might do is just do a separate problem where I say, get the center mass and moment of inertia for a non-uniform rod. And then just to see if you can actually get both of those things right. But it would be very easy to just do the same exact problem with no applied force and just say it's a non-uniform rod and make you figure out the angular acceleration at the instant it is released. Got it?
Are we ever gonna do friction at the axis, or is that something later on?
If you had friction at the axis, usually that is covered usually in a statics class.
Okay.
And so they say there's a frictional moment at the axis. But yeah, if you wanted to, you want to know how to handle it, I'll show you. Look at work page 70. So normally I have you do this in class, page 72. Whoops. Top of page 72. Feel the torque. Imagine this. Imagine you take some PVC pipes bolted together and do that. And then the idea is I could hang a mass on here like this. And this is normally where you get to actually feel the torque. All right. And so then what you try and do is your hands are trying to grab this. Let's say your hands are like these weird spider claws here. Okay. That's supposed to be a hand. skeleclaw or something, right? If you try to hold this thing, you are exerting a frictional force on the axis. Agreed? It's like me. Whoops. Go to here. It's like me trying to keep this thing from twisting by compressing my fingers into the threads and holding it really tight so that it's harder for it to twist. I am exerting a frictional force. And so how do you handle that? Well, then you have to zoom way in and say, well, look, this has a finite radius, right? And so then you could say, well, there's friction on this side and friction on that side. And you do an RF for the frictional force. Piece of cake. Got it?
No, but it's okay.
Oh, okay. How about I?
No, it's all right. I mean, if it's covered in the future classes,
Future
it's not,
classes usually when I
Yeah.
do that one. So did I say more here? So this is oftentimes how you draw it. You just say, look, there's a torque exerted by the pivot, and you just stick in a curled arrow like that. And oftentimes that's the thing you figure out. You see that? So you could figure out the torque on the pivot to keep it from twisting. So far, so good?
Yeah.
And then the idea is the farther out you put the mass, the more torque your hands have to exert to keep it from falling down, which means you need more friction. So that's generally speaking what those types of things end up looking like. So usually what we do is we assume it's negligible. And then in the real world, you build something and there always is some friction. And then you take that into account when you prototype something. So when you actually build something, that's when you just kind of account for the friction by trial and error. And it's usually small, so your calculations are approximately correct. Good enough?
Yeah.
That's just the real world. Yeah. All right. These problems right here, I really like them. The 10, 40, 41, and 42. I'm going to let you do those at home. And it's just getting used to these FBDs where you don't just show arrows touching a dot, you show the arrows where they act on the object. And so you could go through these, don't overthink it. They all have equal magnitude F, and you just do the math and say which, for example, one of these I think experiences no rotation. Do you see which one of these three figures at right will experience no rotation?
The middle one.
The middle one, right? Think about it. This one creates a torque going that way. This one creates a torque going that way about its center of mass. However, this one, notice if one force points up and one force points down, like frictional force on one side pointing down and frictional force on the other side pointing up. And in fact, all of these tend to twist it, right? And so you can kind of get some feelings for that. And then what about this one? You could do the math on it later. And so just do those problems. Trust me, they're worth doing. Look at this one. We started out this chapter by talking about angular kinematics. Here's a plot of omega versus time. What is something that you can get from omega versus time plots that relates to torque? I could think of two things you can get from an omega versus t plot pretty easily. What's one of them?
You can get theta.
You can get delta theta. Does that relate directly to torque so far as you know right now?
No.
Okay. What else can you get from an omega plot?
Alpha.
Okay. And how do you get alpha?
Alpha would be the derivative.
Which is the same thing as saying the
slope.
Slope, right? Okay. And then how do you get delta theta, just so I have it?
It's the integral.
Or the area, right?
Mm-hmm.
So if we needed to get torque, notice you could get one piece of information for sum of torques equals I alpha from an omega versus t plot. Imagine doing a tracker video on something that's rotating. you could get the data for omega as a function of time, get alpha, and learn about the torque required to cause such a rotation, right? Does that make some kind of sense? I'm tingly all over. This is exciting stuff because you're able to start putting together all these pieces and see, oh, all those little basics that I hammered into you and said, do shitloads of problems. I was doing that so that now you could kind of see this. I hope this is kind of cool. It's not easy to do physics. You have to punish yourself and suffer before you can enjoy it. But I think you're at that point now where you could start to slightly enjoy it. All right, so here you could figure out all that stuff. Toilet paper, if you're curious, this is good to read about. Just read that. It's kind of fun to think about. There's one where there's a frictional torque, if you care, Esteban. All right, so we talked about this one. Ooh, all right, so I've got just enough time to show you a couple of cool videos before we get to the quiz, because you're probably faded out your brain. So let me make sure I can have these videos up. Let me get to this one. Let me bring it over here so you can see it. Whoops, I hit the wrong button, I think. Okay. Okay, and so, oh, whoops, that's a different chapter 10. That's a wrong one. Oh, shoot, I need to go to this one. Sorry, I've been keeping the demo videos separate from the lecture videos. Those are my chapter 10 videos from last semester. Oh, sweet. I could just give you those if you want to watch them this weekend and get ahead. I'll try and do that later. Oh, whoops, I forget I have to click this and then click my channel. Sorry, I'm wasting your time here. I'm not trying to. Playlist. There we go. This chapter 10 is like the demos. Sorry about that. It's my attempt to do file management. So look at this. What is this? What pennies on a meter stick? Now, in this case, let me get it up here. This is coupled to this problem. So let's look at this problem. You have a meter stick. It's pivoted at one end. It's held parallel to the floor. A number of pennies are laid out on top of that meter stick. The meter stick is released from rest. So I know you can go through this at home later in more detail. So I'm going to go to the solution at risk of maybe hurrying through it. So there's the video if you need to see it later, okay? I think that link works. All right. So the idea here is, here's the forces on the rod. There's a reaction force at the pivot. There's mg down. This is going to rotate this way when you let go of it because this does no torque. This does a, what direction is that? Clockwise torque. And so this gives you the angular acceleration of the rod. This is the torque. This is I, 1/3, and this is alpha. Now, in this case, imagine you're sitting here some distance x from the pivot. So let's say you're sitting out here some distance x. Well, the acceleration of that point is x times alpha. Why? Because A tangential to the curve. It's not your alpha. It's R alpha, where R is the radius from the pivot. So in this case, if our radius has the name X, we see that, great, this is cool. Now, this is what's crazy. Look carefully here. If X is bigger than 2/3 L, if X is greater than 2/3 L, the acceleration is larger than G. What I'm telling you is points close to the rod are going to fall at a small acceleration. Points near the end of the rod are going to accelerate faster. Does that seem impossible or plausible, or any questions about that?
The only place that experiences G is the center of mass, so I guess that makes sense.
No, the center of mass does not fall at rate G. 2/3 of the way falls at G. I could prove this to you with the demo video. if I
Okay.
can find it. Watch this carefully. Did you see that? I'm going to slow it down even more. Okay, I'm going to pause it at just the right time. Do you see that? Look at the pennies that have separated.
So why is that?
It's because this is not in free fall, but this point of the rod. So this is basically this spot right here is approximately 2/3 of the rod's length, right? And what I just showed you was for points less than there. Remember, alpha for the entire rod is 3/2. What is it? L over G? No, G over L. Sorry, I should have read the equation better. I had it written down, but I think it's this. Does the units check out? They look like it. So the idea is that's the angular acceleration of the rod, the rate at which the rotation speeds up, because there's gravity here, but this is not free fall because the pivot is exerting a force upwards. So the points close to the pivot don't accelerate downwards as fast as points near the end of the rod. As a result, there's some tension in the rod pulling it that way, which causes this circular motion. Let me undo that last picture. But the idea is, look at the over-under. If the acceleration is given by R alpha, that means it's equal to R times 3/2 G over L. If you plug in 2/3 L right there, that's the changeover point where the acceleration exactly equals G. I don't know if you can see this at all, but is that addressing your question?
Yeah, sort of.
Do the math later and it'll make a lot
Okay.
more sense. Do the
Okay.
problem. And I just wanted to show this because we're running out of time. Also, let me show you this other one. I know it's time to take our break. I just want to show you this other one that exemplifies this, because I don't want to lose it. Oh, shoot. I got to escape full screen. I guess it's good we took that mini break. This is the other one that's in there, Faster Than G Part 2. So the ball is below the cup, but it falls into the cup. So when you watch this one, the ball starts below the cup. The cup falls faster than the ball does. The ball is falling in free fall. The ball still goes straight down, but again, I just think this is so cool. The ball falls straight down. We may have had the camera angled a little bit, but yeah. All right. Anyways, that's the idea. In these cases, we see that if you attach one end of a rod to a pivot point, the different points on the rod do not accelerate at the same rate. They have the same angular acceleration. They do not have the same acceleration. All right. That's a good spot